Three-phase power dominates both industrial and domestic electrical supply because it requires less material and delivers superior mechanical performance compared to a single-phase system. In a standard single-phase system, a large return conductor is required to complete the circuit and carry the total capacity of the current. A three-phase transmission line replaces that large return path with a single, significantly smaller neutral wire, which heavily reduces the total volume and cost of conductive copper or aluminum needed for the grid. Furthermore, multiple phases deliver uniform torque that naturally generates a rotating magnetic field, allowing three-phase induction motors to be entirely self-starting from a dead stop. By generating power in 3 continuous waves, engineers cut massive costs on wire gauging and completely eliminate the need for secondary starting capacitors or external starting components on heavy industrial machinery. These mechanical and economic efficiencies are not automatic. They rely entirely on maintaining strict mathematical symmetry across the grid, a condition known as a balance state. This animated graph plots a balanced supply. For the supply to be balanced, all 3 individual voltage phases must share the exact same magnitude, and their wave peaks must be displaced from one another by exactly 120 degrees. This simplified circuit schematic shows a balanced load. A balanced load dictates that the impedance connected across all 3 of these phases must be absolutely identical. Impedance is the total measure of opposition that a circuit presents to an alternating current. When the supply and the load match perfectly, the total power consumed by the system can be calculated using a single master equation. Total power equals the square root of 3, multiplied by the line voltage, the line current, and the cosine of phi. Achieving a perfectly balanced state means engineers do not have to calculate the power of each individual phase and add them up. They can mathematically predict the total power consumption of the entire industrial system using one uniform formula. Because of this exact mathematical symmetry, it is also unnecessary to use 3 separate meters to measure the system's total power output. This technical diagram illustrates the 2 wattmeter method. The potential coils of wattmeter 1 on line A and wattmeter 2 on line C are connected to a common third phase, establishing a shared reference point on line B. These 2 meters are now positioned to capture the distinct voltage and current flowing through the top and bottom branches relative to that shared center phase. This vector diagram maps the underlying phasor mathematics of the reading. A phasor is a rotating vector used to represent a sinusoidal wave. Here, the current lags the voltage by specific angular relationships, specifically 30 degrees minus 5 for the first meter and 30 degrees plus 5 for the second. Because the system is balanced, simply adding the readings of wattmeter 1 and wattmeter 2 mathematically perfectly equals the total 3-phase power equation. This mathematical symmetry allows grid operators to continually monitor total power and determine the system's power factor while reducing the necessary diagnostic hardware by a third. The power factor is the ratio of actual working power used by a system to the apparent power flowing through it. 3-phase power operates as a perfect synergy of physical efficiency and mathematical elegance. The 120-degree offset between phases is the single underlying mechanism that reduces total wiring costs, powers self-starting heavy motors, and simplifies diagnostic measurement down to just 2 meters. By defining and maintaining the exact parameters of a balanced system, industrial power grids extract maximum mechanical output with a minimal physical footprint.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.